2 years ago, humanity did something it had never done before. We deliberately crashed a spacecraft into an asteroid and changed its orbit. But here's the question that kept scientists up at night ever since. What did we actually do to that rock? What does it look like now? Well, the wait is over. ESA's Hera mission has arrived at the Dimorphos system, and what the spacecraft found has genuinely rewritten what we thought we knew about asteroid deflection. Welcome back to the channel. Today we are diving deep into one of the most consequential missions in the history of planetary science. This is not just a story about hitting an asteroid. This is a story about the future of life on Earth and the cosmic detective work that followed the most dramatic experiment humanity has ever conducted in space. Let's set the stage. Back in September 2022, NASA's DART spacecraft, the Double Asteroid Redirection Test, slammed into a small moonlet called Dimorphos at roughly 6.1 kilometers per second. That is about 22,000 kilometers per hour. The impact sent a plume of rock and dust billowing out into space that was visible from Earth-based telescopes, and crucially, it worked. DART shortened Dimorphos' orbital period around its parent asteroid Didymos by about 33 minutes, far more than scientists had predicted. It was a triumph, but it also raised a profound question. What exactly happened to the asteroid itself? That is exactly what ESA's Hera mission was designed to answer. Launched in October 2024, Hera is essentially the forensic investigator arriving at the crime scene. It carries a suite of cameras, radar instruments, and two small CubeSats, miniature companion spacecraft called Milani and Juventas, that can get up close and personal with the asteroid in ways a main spacecraft simply cannot. Hera's job is to map the aftermath of DART's impact in extraordinary detail, measure the mass of Dimorphos, study its internal structure, and help scientists understand exactly why the deflection was so much more effective than expected. Now here's where things start to get genuinely fascinating. When Hera's cameras first resolved Dimorphos into a clear image as the spacecraft closed the final kilometers of its journey, scientists noticed something immediately striking. The impact from DART had done more than leave a crater. The entire shape of Dimorphos appears to have changed. Before DART, ground-based radar and early observations suggested Dimorphos was roughly oblate, like a slightly squashed sphere, about 170 meters across. What Hera is revealing now suggests the asteroid may have been significantly reshaped by the impact. Some researchers have described early observations as showing a more elongated, distorted form, almost like the asteroid was squeezed and partially collapsed by the sheer violence of the collision. This tells us something profound. Dimorphos was not a solid rock.
It was what scientists call a rubble-pile, a loose collection of boulders and debris held together by gravity and weak cohesive forces, almost like a pile of gravel floating in space. When DART hit it, the asteroid did not just get dented, it shuddered, it shifted. It may have fundamentally reorganized itself. Here is the perspective shift I want you to sit with for a moment. We tend to imagine asteroids as hard, solid, ancient boulders hurtling through space, monolithic, unchanging. But many asteroids, especially smaller ones, are more like cosmic snowballs made of rubble, loosely packed, fragile in ways that solid rock is not. And that means when you hit one, the energy transfers differently. The ejecta, all that material blasted outward by the impact, acts almost like a rocket exhaust, amplifying the push far beyond what the physical crash alone would produce. This is what scientists call the momentum enhancement factor, and at Dimorphos, it was significantly higher than models predicted. In other words, rubble-pile asteroids might actually be easier to deflect than we thought. That is extraordinarily good news for planetary defense. Hera's CubeSats are now taking this investigation to the next level. Juventas carries a low-frequency radar instrument that can actually peer beneath the surface of Dimorphos, the first time in history we have attempted to radar scan the interior of an asteroid from orbit. What it finds could tell us how deeply the shockwave from DART penetrated, whether internal fractures were created, and just how loosely packed the interior structure really is. Meanwhile, Milani is studying the dust and debris environment around the asteroid, because there is still material drifting around Dimorphos from the impact, like a slow-motion cloud of cosmic shrapnel hanging in space 2 years later. Every grain of that debris is a data point in understanding what happened. And let us talk about the crater. Ground-based observations after the DART impact had already given scientists hints about the crater size, but Hera's close-up imaging is providing something far more detailed. Early high-resolution images suggest the crater is significantly larger than the minimum predictions, potentially 70 meters or more across, which on an asteroid only 170 meters wide means DART essentially punched a hole roughly the size of a football pitch into a rock not much bigger than the Great Pyramid of Giza. That scale is staggering.
The crater walls, the ejecta distribution pattern, the way boulders have been displaced and rolled, all of this is being meticulously mapped and will feed back into planetary defense models for decades to come. What makes the Hera mission so much more than just a follow-up survey is what it means for the future. Within the next century, astronomers estimate there is a non-trivial probability that asteroid Bennu, a 500-meter rubble pile currently tracked by NASA, could pose a threat to Earth.
And there are thousands of other near-Earth objects we are still cataloging. The knowledge Hera is gathering right now, in real time, is the knowledge that could one day form the blueprint for a genuine planetary defense operation. We are not talking science fiction. We are talking applied science, tested, verified, and ready to scale. Hera is turning the DART experiment from a dramatic headline into a reliable engineering principle. There is something deeply moving about this mission if you let yourself feel the full weight of it. For the first time in 4.5 billion years of Earth's history, a species that evolved on this planet has developed the ability to reach out across millions of kilometers of empty space and deliberately alter the trajectory of a natural object. We moved an asteroid, and now we have sent another spacecraft to understand exactly how and why it worked, so we can do it again, better if we ever need to. Dimorphos is no longer just a rock. It is a monument to human ingenuity, a testament to international scientific cooperation, and a proof of concept for our species' long-term survival in a universe that is, frankly, full of hazards we did not choose. The cosmos does not negotiate, but thanks to missions like DART and Hera, we are starting to learn its language. The data from Hera will continue flowing back to Earth over the coming months and years, and every new image, every radar scan, every CubeSat flyby is going to add another layer to this extraordinary story. We will be covering all of it right here, so make sure you are subscribed so you don't miss a single update. If this video blew your mind even a little bit, hit that like button. It genuinely helps us reach more curious minds out there in the universe. And drop a comment below. What question would you most want Hera to answer about Dimorphos? I read every single one. Next time, we are exploring something equally jaw-dropping: the strange, violent death of the most massive stars in the cosmos and the exotic objects they leave behind. You're not going to want to miss it.